most suitable material for the tray, functions, objectives, constraints, and free variables are identified. The function of the tray is to be light, strong, and stiff to provide better performance of the overall EV and to hold the battery in its place safely. The objective is to minimize the mass to increase the efficiency and minimizing the cost such that it would be commercially viable. These are the constraints. The dimension of the tray should fit the battery. Young's modulus needs to be greater than 60 gigapascals to avoid failure due to fatigue loading for 5 years, and estimating that the tray will go through 10 million cycles. The endurance limit of the material has to be approximately 100 megapascals. It requires good corrosion such that it lasts minimum 5 years. The maximum service temperature has to be greater than 70 degrees Celsius, as the optimal temperature of the lithium battery is up to 55 degrees Celsius. Three variables are the thickness of the panel and the choice of material.
We used Ejipack to optimize for the ideal material. We made a few ballpark calculations to find the upper bound of the Young modulus, yield strength and fatigue strength required, as well as inputting minimum service temperatures, humidity resistances, and flammability to screen unviable materials. Choosing only non-ferrous metals meant that materials wouldn't rust and wouldn't interfere with the battery's magnetic field, and after this screening, we are left with around 32 metals to choose from. For each of our constraints, we used material indices to minimize the mass and the cost. These two conflicting objectives were plotted against each other for every constraint. The penalty function was thus created with an alpha value of 1, valuing both cost and mass equally. The most viable materials were on the lower left quadrant, closest to the penalty functions. Aluminium alloys and magnesium alloys were the most viable, but we boxed out magnesium for their inferior corrosion resistance. Of the aluminium alloys, the two best were 6010 and 6061, but we opted for the former due to its superior yield strength.
To manufacture a battery tray made out of aluminium alloy T6, the primary shaping manufacturing method have been ranked in terms of their cost. Primary shaping is used to shape the raw material into a basic form such as a plate or panel. To produce the graph on Ejipack, we set certain limits to control the variables. The primary shaping method most suitable is forging. This is because it is relatively cheap and can be done on the chosen material. All other methods shown are either more expensive or they cannot be done on aluminium. Once the aluminium is forged into a basic shape, it should be milled to form specific components. These components should be welded together to produce the final tray. The aluminium cost roughly £2 per kilogram. The cost of manufacturing through the manufacturing method mentioned is £18 per unit, relatively.
For the analytical solutions section, we decided to study 4 different load cases. The first load case was where a static load was applied to the base of the tray from the battery. This situation would occur when the vehicle is stationary. The tray was assumed to be a simple beam so that ballpark calculations could be made. Taking the mass of the tray itself as 100 kilograms, the static load was estimated at 400 G. The maximum deflection found in the base of the tray from this load was 0.18 millimeters. The second load case had a dynamic load applied to the back wall of the battery tray. This situation would occur when the vehicle is moving up or down a hill. We assumed that the hill had a steep gradient of 30 degrees. By resolving forces and using Newton's second law, a maximum deflection was estimated to be 0.021 millimeters. For the third load case, where a vehicle would drive over speed humps and potholes, a dynamic load was applied to the base of the tray. Many assumptions were made about the reckless driving that would cause a worst-case scenario, as well as the dimensions of any speed humps or potholes. Using kinematic analysis, a force of 62 kilonewtons was calculated. However, this load force was reduced to 25 kilonewtons when using beam analysis, due to an assumed dissipation in the suspension and wheels. The maximum deflection of the base was found to be 0.52 millimeters. For the final load case, a dynamic load was applied to the sidewall of the tray. This would occur when the vehicle is turning around a bend. The vehicle is assumed to be traveling at 40 km per hour and around a bend of radius 5 meters. After beam analysis, the maximum calculated deflection was 0.056 millimeters.
To begin with, an initial design was modeled in Fusion 360 based off the design criteria diagram. It has a total of 10 bolts to secure the tray to the bottom of the car. This gave us a weight of 350.9 kilograms where it is made from aluminum 3010T6. The design was then put through topological analysis to optimize mass on the load. The bolt holes were preserved and constrained, and location pins were also preserved. As seen from the colored diagram, a lot of the material was found to be unnecessary for an acceptable minimum safety factor of around 3 to 4, and therefore a new design was created from this analysis. It has square plate protrusions for the bolts and location pins from the base tray with triangular trusses and weighs 54.1 kilograms when modeled with aluminum 6010. We then put this model through simulation testing in different load cases. We used a slightly higher load than actual for further safety. For load case 1, the load of the battery is applied to the base of the tray and the maximum deflection is 3.29 millimeters. For load case 2, with a constant acceleration dynamic loading of 5.5 kilonewtons applied to the latitudinal inside wall of the tray, the maximum deflection is 0.54722 millimeters. For load case 3, with going over a bump, there is a dynamic load of 25 kilonewtons applied to the base. The maximum deflection of the base is 24.79 millimeters, and the model has a generally low safety factor of 0.845. And for load case 4, during turning, there is a load of 3,500 kilonewtons applied to the longitudinal inside wall of the tray.
We then proceeded to start the generative design using our second design iteration as base model. We started by designing the obstructions representing the battery slot in the car's underbody and the battery's geometry itself, in order to prevent the AI from altering the tray's design into that space. We then constrained all the bolts and guide pins before selecting the relevant manufacturing processes. These were unrestricted, 2.5-axis milling and 3-axis milling respectively. This gave us a total of 5 generative designs, including 2 of them which failed. We ended up choosing the one produced by the 2.5-axis milling due to its lighter weight and cleaner look. We then proceeded to run load tests for each case, and the peak deflection occurred in load case 3, where the car went very fast over a hump, for which we estimated a peak dynamic loading of around 25 kilonewtons. The bottom plate for this load deflected 6.5 millimeters downwards from its center. Since this was an unacceptable deflection, we chose to modify this generative design by implementing a honeycomb lattice structure at the base. Standing 10 millimeters tall and sandwiched between the bottommost plate and an upper plate located just beneath where the battery sits, each of them 2 millimeters thick. So we then ran the load tests again, and the results are shown on the screen. For the first load case, we recorded a maximum deflection of 0.19 millimeters. For load case 2, we recorded a maximum deflection at the back wall of 0.031 millimeters. For load case 4, a maximum deflection on the side wall of 0.019 millimeters. For the peak estimated dynamic load, we observed a 78.5% reduction in deflection compared to the previous iteration produced through generative designs at only 1.4 millimeters. However, due to the very short duration of this loading in real life, estimated at 0.04 seconds, we expect a much lower deflection. So all the aforementioned arguments, combined with the fact that this version meets all our design criteria, such as weight and manufacturing cost reduction, while exhibiting very good mechanical properties, is why we chose this iteration as our final design. Thank you.